In this lesson, we're still going to talk about volumes, and we're still going to talk about volumes that are found by using regions in the plane. But when it comes to cross sections, we don't revolve anything around a line in the plane. Here it says, let R be the region in the first quadrant under the graph of y equals 8 over the square root of x over the interval from x equal 1 to x equal 8. Find the volume of the solid whose base is the region R and whose cross sections, which are perpendicular to the x-axis, are squares. So volumes by cross section look a little bit differently than volumes of revolution. So volumes by cross section, that's what we're going to talk about here. So let's illustrate, let's find this region R. We're starting at x equal 1, not at x equal 0. So there's x equal 1. Here's x equal 8. So here's the region in the plane that we're talking about. Now again, we're not going to pick this region up and spin it around the x-axis or the line x equal 1 or anything like that. We're just going to consider it the base of some three-dimensional solid. And specifically, it's a three-dimensional solid that if I took a cross-section, if I started at some random point here on the curve and went vertically straight down to the x-axis, the cross-section of that three-dimensional solid perpendicular to the x-axis would be a square. So I would have, if you can imagine this coming up off of the slide or out of the video into the space in front of you, spatially, hopefully you can see there's one representational cross-section of this three-dimensional solid. Now I'm going to move to the next slide to kind of show you here is what we're talking about. Again, here is our region in the plane. There is x equal 1, here is x equal 8. So there is our region R in the plane that is the base of our solid. So imagine this three-dimensional solid that's sticking out from the page, and all the cross sections are squares that are perpendicular to the x-axis. That's what those words mean. Cross sections perpendicular to the x-axis. And I have several representational squares drawn here that are perpendicular to the x-axis. So that kind of gives you an idea of what the three-dimensional solid might look like. So let's see how we find the volume of a solid that's made from a region in the plane like that. So you saw that we have infinitely many squares along in here. We have one that has, here's the side of this biggest square, and it's coming off like this, and here's the side of another one and another one and another one. We know that the area of a square is simply identifying what the side is, what the length of the side of the square, and squaring it, or it's side times side, right? Side times side. Well, the beauty part of a square is that all of the sides have to be the same. So if I take this square and I give it a little thickness, now I've actually got a three-dimensional prism here. This square has some thickness to it. Now I'm talking volume, right? If I take the volume of this prism, it is the area of the base, which for us is a square, times the height, or for us I'm going to use the word thickness, of that prism. And we said that the area of the base was side squared. Here we can clearly see that our thicknesses fall along the x-axis, so our thicknesses are going to be with respect to x. And we're used to adding up infinitely many from A up to B, infinitely many things. If we're finding area, we did that using rectangles. We added infinitely many areas of rectangles, starting at A, stopping at B. If we had volumes of revolution, we added the volume of either the disk or the washer. We found one representational disk or washer, and we wrote the integral from a up to b so that we were adding up infinitely many of those. We're going to do the identical same thing here. If we could find one representational cross-section, one prism in this case, which is the area of the base, which is side squared, times a thickness, then we're adding up infinitely many of those cross-sectional pieces, and we're going to wind up with the exact volume of the three-dimensional solid. So same type of idea, just different geometry actually is all that's going on. And again, what's beautiful about a square is that it is as tall as it is long. So if we talk about length times width in a square, or we could talk about height times length, either way we're talking about these two measurements, we're guaranteed that those are equal. So that's why I'm just calling it each one a side. And I want the side, of course, in terms of the function that was given, right? Because that's all I have to go on. So the length of a side in terms of the function, the beauty part here is that this side, the bottom of the square, this square that's lying on the region R in the plane, is the area, the region bounded in the plane in between the function and the x-axis. So that makes the side equal to the function. And I want that squared. So the limits of integration are given to us. We start at x equal 1. We stop at x equal 8. The function is given to us. It's 8 over the square roots of x. It is the area of the base, which is side squared, times the thickness. As far as volumes go using the definite integral, cross-sections are the easiest ones. There's no big R's and little r's or anything like that. It's just basically finding the distance of one side of some sort of cross-sectional piece. Now, not all cross-sections are squares, so we've got to be careful. Our cross-sections can be a lot of different geometric figures. So this is the integral from 1 up to 8. 8 squared is 64, square root of x squared is x, and that is dx. So the antiderivative, 64 times the natural log of x, and we are integrating from 1 to 8. Give myself a little more space here. And so we have 64 times the natural log of 8 minus the natural log of 1. So our exact volume is 64 natural log of 8. So it becomes very important that you pay attention to your function. You have to pay attention to your interval. Those are your limits of integration. And if you are perpendicular to the x-axis, finding, the bounding curve is fairly easy. It's usually the function that they gave you. And the most complicated part, which is hardly ever complicated because lots and lots and lots of volumes by cross-section problems that wind up on the AP test do have cross-sections that are squares. But we're going to work some examples where the base might look a little strange or where the cross-sections might look a little strange. So let's look at this example here. Find the volume of a solid whose bottom face, or whose base, is the circle x squared plus y squared equals 1, and every cross-section perpendicular to the x-axis is a square. So we still have squares as our cross-sectional pieces. We're still perpendicular to the x-axis. Here's perpendicular to the x-axis. But here our base looks a little bit different. Here it's not just the region bounded between a nice looking function and the x-axis. Here's the y-axis, here's the x-axis. So there's a little more work to do on this one, but it's still not that terribly difficult. So if we have cross-sectional pieces, what we want to do is we want to integrate from A up to B. We need the area of one representational cross-sectional piece times the thickness. That's going to give us the volume, right? So it becomes important that we find the area of one cross-sectional piece. For a square, area is side squared. So I'm going to square that. Now I need to find a way to represent the side of that square using the information that they gave me. Okay, and this is where it's just, a little bit different than the first one. The first one was, here's your function. It's y equals blah, 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 blah. Here we have a circle centered at the origin, right? It's not x minus h or y minus k, with a radius of 1. So that helps me know that I'm going from -1 to +1. That tells me what a and b are right away. So I know my limits are -1 to +1. Now I need an upper bounding curve and I need a lower bounding curve, right? Here we don't stop at the x-axis. One side length is from the top of that circle, or the circle that bounds on top, and the same circle that bounds on bottom. So we have a top function and a bottom function. The problem with a circle is that it's an implicit function, and I am integrating with respect to x, not implicit, but explicit. So what I need to do is I need a way of writing x squared plus y squared equals 1 explicitly. What's the explicit function here? Well, the explicit function, if I solve this for y, and I need to be very careful doing it, many students are going to do this. There's a problem with this. This is a square root function, and it's a positive square root function. That is just the upper hemisphere of this circle. So you have identified the upper bounding curve. Not a problem at all. It is the positive square root of 1 minus x squared. But you also need to identify the bottom bounding curve. All right? And that's why when you take the square root of something squared, it yields you a positive or a negative value, because it is true the negative square root of 1 minus x squared will give you y squared. So be careful. So the bottom bounding curve is -1 minus x squared. So be very careful in finding all those pieces. I'm going to clean some of this up a little bit, give myself some more space. Just kind of get rid of the algebra that's going on here. Okay, so now we have a top bounding curve and a bottom bounding curve. So the sides of our squares are the distance from the positive root to the negative root. So one side is the square roots of 1 minus x squared minus, that distance is minus, right? Minus the negative square roots of 1 minus x squared. So actually we could find, if you'll look at this, 2 times the square roots of 1 minus x squared. That's actually what our side is going to be. Our length, which is what that's what we're after here, our side is actually 2 times the square roots of 1 minus x squared. Many of you said already, probably in your heads, why is she even bothering with the bottom half of this? Why doesn't she just worry about the top half of it? Because it's a symmetrical three-dimensional solid. Why doesn't she just take twice the upper hemisphere? Well, she is. That's what this turns out to be. And I don't care either way, you can do it. But I did want to show the students that even if you choose not to do that and choose not to use the symmetry that's going on in that circle, you're still going to wind up at the same place. All right? So the area is side squared. So we're going to square both sides. That's 2 times square root quantity 1 minus x squared squared. And so the area that we're actually going to put into our definite integral winds up being 4 times the quantity 1 minus x squared.